Hello, welcome to another module in this massive open online course. Alright, so in this module, let us start looking at the implementation of IIR filters using various IIR filter structures. Alright, so we are going to outline the structure of these various IIR filters. Okay, and so the title is IIR filter structures, which plays an important role in the implementation of digital filters. And IIR, as you know, this stands for infinite impulse response. To illustrate this, consider the third order filter given as follows. So, we have consider the third order filter given by the transfer function Hz equals P naught plus P1 Z inverse plus P2 Z minus 2 plus P3 Z minus 3 divided by 1 plus D1 Z inverse plus D2 Z minus 2 plus D3 Z raised to minus 3, which I can write as Pz over dz, and remember this is the output Z transform Yz divided by x of z, and this can be implemented as follows. I can write this Yz equals xz into hz, which is xz into pz divided by dz, and this is xz into pz into 1 divided by dz. So, I can call this, implement this as a cascade of two systems. I can call this xz into pz, this can be defined as wz. So, I can write this as wz into 1 over dz, y is equal to wz into 1 over dz, where wz equals xz into pz. So, this is a cascade of two systems, that is pz into 1 over dz. So, hc is the cascade of these two systems. Okay. Now, let us look at, so I have xz given as input to the first system, H1z, the output Wn is given as input to the second system H2z, and this is Wz, and the intermediate signal is given by the Z transform Wz. So, H1z is basically your Pz, and this is your 1 over dz. Okay. And now, let us look at Wz. You can see Wz equals xz into Pz, which is xz into P naught plus P1 Z inverse plus P2 Z minus 2 plus P3 Z minus 3, and therefore, now if you look at that corresponding, if you look at the corresponding time domain expression, already the equivalent time domain difference equation for this, you will get, taking the inverse Z transforms, that will be Wn equals P naught times xz corresponding to P naught times xn plus P1 Z inverse xz, that is xn minus 1 plus P2 Z raised to minus 2 xz, that is xn minus 2 plus P3 x of n minus 3. And the structure for this, it can be given as follows. So, you have the input x of n. So, let me draw it over here. So, I have this is your x of n. So, this is P naught, this is Z inverse, and the element Z inverse, correct, and you are multiplying that by P1, that will give you xn minus 1. So, this is performing the addition of P1 xn minus 1 plus P naught xn, and again going through another element Z inverse, that will then multiplied by this xn minus 2, that is multiplied by P2, and then what you have over here is you take this and you add to this, and finally what you have over here is another element Z minus 3, that you will multiply by the gain P3 and add to the existing, and you can see what you have over here is basically your Wn. So, that is P naught xn plus P1 xn minus 1 plus P2 xn minus 2 plus P3 xn minus 3. So, this is Wn equals your P naught xn plus P1 xn minus 1 plus P2 xn minus 3 P2 xn minus 2 plus P3 xn minus 3. Okay. Now, we come to the second part. So, this basically implements your xz into pz. Now, we come to the next part, that is yz equals wz divided by over dz. Okay. So, we have yz equals wz over dz, which is basically your wz over 1 plus d1 z inverse plus d2 z minus 2 plus d3 z minus 3. Now, once again taking the inverse z transform, this implies that you have yn plus d1 yn minus 1 plus d2 yn minus 2 plus d3 yn minus 3 equals your Wn. Now, this can also be written as Yn equals Wn minus d1 Yn minus 1 minus d2 Yn minus 2 minus d3 Yn minus 3. And now, therefore, I can write this thing over here as follows. I can incorporate the IIR structure corresponding to this as follows. So, Wn minus, now let us look at this, Wn minus, so I have over here, let us say your outcome, that is Yn, okay. Now, I am going to here perform so you have minus dn. So, this is W1 minus dn. I am sorry, there has to be a delay over here. So, that will give you Yn minus 1, correct. So, minus dn Yn minus 1, and this will be minus d2 and pass it through a delay z inverse. So, this will be minus d2 Yn minus 2, and finally, you have another gain here minus d3, and this will be your third delay z inverse. So, that will be minus d3 Yn minus 3. So, Wn minus d1 Yn minus 1. So, at this point you have minus d1 Yn minus 1, at this point you have minus d2 Yn minus 2, and at this point of course you have minus d3 Yn minus 3, okay, and Wn, and this when added to Wn gives you your Yn. So, basically now this part represents your Wz into 1 over dz equals yz. Okay. So, you have implemented it as a cascade of two systems, all right. So, into Pz into 1 over dz. So, this is basically the cascade of two systems, all right, and this is known as the direct form 1, and this kind of realization, all right, this cascade of two systems, all right, this is known as the direct form 1 realization. Okay. So, this is realization is known as your direct form 1, that is your df1, also termed as df1 or df1 realization. Okay. So, that gives you your df1 realization. Now, what you can do is first you can interchange these two blocks. Remember, when you have a cascade of two LTI systems, you can always interchange, that is your H1z, H2z. You can interchange them to have H2z followed by H1z, all right, because convolution is commutative, the resulting system remains unchanged. So, basically I can interchange these two systems. Okay. So, now what I am going to do is I am going to interchange the two systems or interchange the two branches in df1, and what that gives me is something very interesting. When I interchange the two branches, I will have, well, I will have xn, let me just draw this again, and I have an adder, okay, and that will give me z inverse, okay. This will be multiplied by minus D1 added to the previous one, Z inverse, okay, multiplied by minus D2 and added, and finally what you will have is Z minus 3 multiplied by minus D3 and then you have here you have an adder, okay, minus D3 minus D1 minus D2, okay. And now you can here you have Z minus 1, all right. Basically I am interchanging the two systems, okay. So I have Z minus 1 and this will be Z minus 1 and Z inverse that, and first you have here a gain of P naught. So this is your Yn, or let us put it this way. So P naught okay, and this will be P1 and further you have your second delay Z inverse multiplied by gain P2, output of this multiplied by gain P2, and you have another adder, and then you have another element Z inverse. This has to be Z inverse multiplied by, let me just check the delay elements, this has to be, I am sorry, again Z inverse, okay. And therefore now you multiply this by P3, okay. So they will multiply this by P3 and what you have is basically you have the interchanged, alright. So this is basically interchanging of, after interchanging branches of DF1, this is what you have, okay. And what you can realize at this point is that if you look at this pairs of signal points 1 and 1 prime, and if you call this 2 and 2 prime, and finally if you call the signals at these points 3 and 3 prime, these signals at these points 1 and 1 prime, 2 and 2 prime, 3 and 3 prime, these are the same, that is whatever the signal is at this point, alright, let us call this W tilde n. So this will be W tilde n minus 1, W tilde n minus 2, W tilde n minus 3, alright. So basically what that means is I can fuse these two signal points, and therefore the resulting, what that does is basically, the advantage of that is basically that eliminates the duplication of these delays. So I can fuse, I can merge the delays, okay. So basically I can fuse, so the signal points 1 1 prime now these pairs are basically signals this implies the signals at these node pairs are identical. This implies that you can, delays can be shared. Implies basically those signal points can be merged So, delays, these delays can be shared in a common. So, for instance, the delays can be shared, and once you merge these and share the delays, the net after sharing of delays on the common and basically eliminating the duplicate delays, what you have is you have your xn that is basically, so you have your xn that is basically adding, and you have your point, you have z inverse, okay, and this is multiplied by again p naught, again there is an adder here, and you have yn, and now here from this itself, this node itself, you can have two branches or two out. So, this is minus d1 and this part here is basically your p1 and this is basically what is giving you this. And now you can have, you have another delay which is basically because you have merged the nodes 2 and or 2 and 2 prime, and this gives you p2 and you have an adder here, and similarly you have an adder here, and you have a gain of minus d2, and then you have this point, and finally you have this point here z inverse p3 and you have minus d3, another adder, and then you have this thing. Okay. So, basically now you have what you have. So, this was previously, for instance, I think let us look at this point. This was previously 1 and 1 prime. So, this was merging 1 and 1 prime. So, basically I am representing it by this symbol 1 and 1 prime. This is after merging 2 and 2 prime, and this is after merging 3 and 3 prime, and what you have is, so the 6 delays have become 3 delays, and basically this is termed as the direct form 2 realization, df2 df2 or the this is termed as the direct form 2 realization. All right. So, previously what you see is we had here we had df1, notice we had 6 delays. Okay. So, notice here we had 6 delay elements. All right. So, there are 6 delay elements here, and from this 6 delays what we have here is we have only we have managed to reduce this to basically 3 delays by fusing them suitably. So, what we have managed to do is we have reduced it to reduce the delays by a factor of half. From 6 we have come down to 3 delays. Alright, that is the advantage of the direct form 2 realization. Alright, so in this module we have started looking at the direct form, that is the realization of various IIR filters. Alright, we have looked at the direct form 1, direct form 2 realization, and we will continue with other realizations in the subsequent modules. Thank you very much.